Hello YouTube, this is Dr. Ronald W. Satz, founder and chair of the International Society of Unified Science and president of TransPower Corporation, a commercial and custom software manufacturing and certified systems engineering company. I work as a theoretical physicist and as a systems and mechanical engineer. Today, as with most of my screencasts, I'll be discussing the reciprocal system of physical theory. You can see on the screen, on the left panel, you see the main menu of the Microcosmos database, and on the right panel, the Macrocosmos database. I've already covered all the topics here, the layouts here in the Macrocosmos database, and I'm in the midst of covering the topics here in the Microcosmos database. We've covered this, all these solid matter properties, and now we're going to talk about energy and entropy for liquid, vapor, and gas matter properties. So let's click here, and up the layout comes. A lot of stuff here. I have this divided up into a liquid section here, a vapor section here, and a real or ideal gas here. Okay, the top row here, same as all the other layouts in the fluid set of properties. We have the element, compound, or mix. It's H2O. This is our sample that we're working with. It's ice, water, and steam, of course. Form number 1, atomic molecular weight is here, melting temperature is here. This is the observed temperature. Vapor gas symbol is the same in this case, but it could be different for some other substances. And atomic molecular weight is here. There's no delta V factor here, but it might be non-zero for others. Calculate the melting temperature K here. You can see it's the same, it's exact. The heat of fusion is calculated here, joule per mole, and well, here, let's see what this is. The heat of fusion equal to the enthalpy of the liquid at the melting point, the enthalpy of the solid at the melting point. And this is the calculation of the heat of fusion takes into account that only, here, let me read this, only a fraction of the molecules at the melting point are in the solid state, and which therefore need to be heated to change to liquid. The remaining fraction of the molecules are already in liquid state. Okay, that's the difference. And so here's the observed value. It's pretty close. Pretty close. All right. These are the structural parameters, this whole list here. I've gone through this before in other screencasts, but it's essential that you understand that. These are not fudge factors or regression coefficients. These are actual structural constants for the substance under consideration, in this case the liquid water. So here we have, that's odd, there should be a pop-up there. A number of elements is 2. Number of atoms, obviously 3. Oh, look at that. I don't have the tooltips for these. Oh well. NS1, NS2, N initial, N internal. These are the liquid thermal groups here, 1.5. Structural groups, 1.5. Number of volumetric units, 1.5. Number of temperature units, 2. Number of pressure units, 9. That means 9 molecules act together to act against external pressure. And this is the CCP average, and cal per mole K, 3R. And here we have the external pressure. This is an important input. Once you have all this in, you're basically just going to put in the external pressure once, and then you have the temperature here that you want to deal with for the liquid, or the temperature here for the vapor, or the temperature here for the real or ideal gas here. Now you can choose absolute or relative values, and I explain this. Remember, always make use of the tooltips. You hover the mouse over there. Relative enthalpy for liquids and vapors is based on 0 at the melting temperature. I'm going to get through this. Okay, so relative enthalpy for gas is based on 0 at the critical temperature. Okay. Note, other authors have different definitions. Relative Relative entropy for liquids and vapors is based on 0 at the melting point. Relative entropy for gases is based on 0 at Tg, the temperature of the gas at the two-dimensional limit, and let's go again. Or TL0, okay? Alright, so here's the temperature input, 600K. Now, for comparison to the theory, I do supply you with the Yaw's regression coefficients. Carl Yaw's book, Chemical Properties Handbook, is very important to have on hand to compare with the theoretical calculations, because you have to have some way of comparing the theory to the experiments, and you don't want to look at just a list of data points. And of course, these have been entered in from other screens. These are SI values. Alright, anyway, if you want to set TK to the mean of the sink in the source, you can click that. That's, option. You can also use the vapor pressure as the external pressure. It's no, because put it here. Alright, so now we calculate enthalpy, internal energy, entropy, cal per mole K, temperature. Well, this is another section here. It's heat sink, heat source, and the delta. But let me just go through these. So enthalpy in cal per mole, joule per mole, cal per gram, and then enthalpy from Yaw's. So you can see, you can compare the different values here. Internal energy, cal per mole, joule per mole, cal per gram, and then again from Yaw's. And the entropy, cal per mole K. Well, that's what that really is. Okay, so these are really for the energy, but this is just strictly cal per mole K, or joule per mole K, cal per gram K, and then entropy. Okay, all right, and then we have the usual stuff here with heat sink and heat source. So this is the that's the melting temperature, really. Okay. So we're using relative values, so naturally these are 0 here. So then we have the heat source calculations, and we go through the whole thing, the rest of it here. Okay? So anyway, once you work out what these values are here, and they're just directly copied over from the previous layouts. That's why there's really no tooltip here, because you're not changing the values from the previous screen. So for example, if I go back, let's just click here for me, back to specific heat. Yeah, this is where you enter them. So I'm just going to read these off again, just so that it's clear. This is the number of elements, obviously H and O in this case. Number of atoms, 3, obviously. Number of close packed groups per molecule in the solid state. Number of close packed groups per molecule in a liquid state. And this is a little bit strange here with these fractions. It's unusual, but that's because of hydrogen bonding and water. Then we have the number of initial units extrapolated back to 0K for specific heat of the liquid. Then we have the number of structural groups having internal motion, solid-like vibration per molecule, that's 0. Number of liquid thermal groups per molecule, number of liquid structural groups per molecule, number of liquid volumetric units, number of liquid temperature units, number of units, atoms, or molecules resisting external pressure. Okay? So then if I go back to energy and entropy, they're already all there. Okay, so that takes care of the liquid state. Let's go to the vapor state. Again, you put in the temperature here. By the way, this is a pretty high temperature, but it's a pretty high pressure. That's why you will get some liquid. But suppose you're dealing with a vapor temperature 410. And here we have the vapor pressure calculations answer. In this case, it's 2.062. And we get enthalpy is this line here, and internal energy is this line here, and then entropy, cal per mole K, joule per mole K, cal per gram K. Right? See, up here it's the same thing, but etc. because there's no room. But here I have room to state it clearly. Enthalpy vaporization. Then I compare this with yaws. Let's see what I say anything here. Okay, not sure about this right here. Available energy, cal per mole, unavailable energy, Carnot efficiency, available effectiveness. Okay. Anyway, I guess that takes care of all of these. It's interesting. Alright, so this is the vapor section here, and enthalpy vaporization. Pending clarification, the reciprocal system will use the yaws. Yeah. For this particular number, I'm using the same value as yaws for the enthalpy vaporization because we don't have that available yet in the reciprocal system. Okay, it explains that. Alright, so now we have this string of values here, and this is the same really as on the other screen. So let's go back to specific heat and go back through that again. I just think it's important. The initial level in terms of natural temperature units for 2D and 3D gas temperature, normally this would be 2/9, if not enter decimal, so it's normally 2/9 there for I underscore T. Then we have the number of thermal groups in gas at the 2D gas initial point, 1.3. Number of thermal groups in gas just before going to 0 at 3D gas initial point or beyond, okay? This is temperature of the liquid at the very beginning of the transition to gas. And this, TG, 2D, 0K, this is the temperature at 2D gas at initial point K when internal motion leaves liquid state and assumes the status of a 2D gas. Now notice the program calculates these things, but I just want to make sure you understand that all this has to be calculated in order for us to calculate all the other parameters of the specific heat, and on the other layout, the energy and entropy. TG2.5D 0K. This is the temperature intermediate between 2D and 3D gas. Temperature of 3D gas at initial point K when internal motion reaches the 3D state. Okay? Program calculates all of this. And then here's the calculation method for specific heat. There are different methods. Okay? Alright, well anyway, let's go back to energy and entropy. And here are all the numbers here. So I'm just telling you, these parameters here all come from the specific heat layout. Now you input the temperature K for the real gas, 1000, and the pressure in atmospheres here, okay? In this case, same 500, or 500 up there. We have the yaws regression coefficients for the gas here. Again, it comes in from the other screen, and then we have the calculations. Cal per mole K, joule per mole K, cal per gram. This enthalpy, internal energy, entropy, Cal per mole K, etc. here, and then these are the corresponding yaws values from the empirical regression equation. So they should be pretty close, and if you look, they are, which verifies the theory. Because we use actual structural parameters to do the calculations, not empirical regression coefficients, okay? I just want to make that very clear. Quantum mechanics has no theory of the liquid, vapor, or gas state. And it has a hard enough time doing anything with the solid state as well, for that matter. And then, of course, we have the heat sink and heat source, just like we do for the liquid state up here. So then we calculate enthalpy, enthalpy yaws, internal energy, and entropy. And you can compare the two. So you can see they're very, very close. It's very nice. And then the delta, the change. Okay? And this is if you wanted to set a TK to mean of the sink and the source, which, well, let's just do that. I suppose I'm going to do that. Take a little bit of time. So that's 850. And of course, then, that changes some of the other values. That changes this value up here to 850. If you want to look at the mean. All right. I think I'm going to read this note here. I think it's important. The real gas volume at the critical temperature and pressure is 2/3 of the ideal gas volume. At those same conditions, it's a 2D gas, okay? 2D versus 3D, 2/3. Also note that in the reciprocal system, the liquid viscosity is constant, whereas it is not for the Gauss regression equation. The estimated saturation volume using an empirical equation is taken at 647.12 K rather than at 647.13 K due to numerical issues. Interestingly, this simple vapor volume calculated by the reciprocal system for water at the critical temperature and pressure is equal to the saturated volume. But this is not the case with other vapors, hence a purely theoretical calculation cannot be given. Presently, the Gauss regression equation does not go to infinity as it should at the freezing point. Reciprocal system viscosity values are considerably high. Well, we'll get to viscosity in another screencast. All right. Just before leaving this, I just want to emphasize this again. This is the liquid section here, the vapor section here, and then the real ideal gas section here. So, again, these are structural parameters for the liquid, and these are structural parameters for the gas. And let's see. Well, I think we've covered most of these, if not everything. All right, I'm going to close out. Now, I should point out, you know what I'd like to do now? I'd like to go, let's just take a look. Let's minimize this. Well, actually, let's see. What can I do here? What if I minimize that? Let's go to Acrobat. And let's go to Existence, Interactions, Computational Treatise of the Reciprocal System, the True Theory of Everything. So let's go, and let's go to, say, liquid state. I just want to show you the paper. Let's go to next. See if I can find this paper, this part of the work, quickly. All right. Yeah, if you really want to understand, let's do Control Plus. If you really want to understand the database, you need to read this paper, In Existence and Interactions, a computational treatise of the reciprocal system, the true theory of everything. Now I'm going to just page down. I'm just going to skim through this paper just to give you an idea of what's involved. I mean, just look at the calculations here. I have graphs, of course. Discuss the odds equations. I mean, it's just page after page of equations. Here's like the water liquid absolute entropy, and that compares with the Yaws equation. You can see it's pretty close. Alright, I think that's enough for that. But I just wanted to show you this paper that, you know, all the calculations are explained in detail in this paper. So, you know, let's get out of this now and go back to the database. Alright. Well, that wraps it up for today. Please study the reciprocal system and prove it for yourself. The simplest possible treatment of the theory is in my very first work, The Unmysterious Universe. Has all the concepts, many diagrams. It's mostly text, very little in the way of math. But if you do want all the mathematics, please obtain my work, Existence and Interactions, a computational treatise of the reciprocal system, the true theory of everything. Thousands and thousands of equations, 711 pages for the PDF, 711 slides in the PowerPoint file. Numerous diagrams, tables, figures, everything. It'll take you months to go through it. Then, after that, then you can get these two database modules. This is the Microcosmos database module, and this is the Macrocosmos database module. The Microcosmos database module covers solid matter properties, including interatomic distance, valence, specific heat, energy and entropy, thermal expansion, compressibility, electrical and magnetic properties, isotopes, and atomic spectra. The liquid vapor gas matter properties covers volume and density, specific heat, energy and entropy, which we covered today, viscosity and surface tension next week, electrical and thermal conductivity. And it also includes cosmic elements and subatomic particles, including material and cosmic subatomic particles, and of course photon properties. Over here on this side we have the Macrocosmos database, which I've covered in screencasts before. The universe as a whole, galaxy clusters and groups, galaxies, star clusters, stars, planets, moons, minor bodies, nebulae, gas and dust, events and voids. Has a good graphics program, so does this Microcosmos database. Covers star graphs and general progression gravitation graphs. Okay. Now, my theoretical physics mentor, Dewey Larson, is also a theoretical economist, and I've made his work in economics also fully computational, just as I've made his work in physical science fully computational. My software program, Optimal Economist, an implementation of Larsonian econophysics, covers the microeconomics of individuals, businesses, and business sectors, and the macroeconomics of entire regions and countries. Completely supersedes Keynesian economics. It's way, way better than the economics you learned in college or high school, for that matter. But it's fully computational. We'll be doing some screencasts on that probably in the summer sometime. So it's coming up. Alright, well, again, please study the reciprocal system and prove it for yourself. And as usual, thanks for your attention. How do I shut this down?